Hello, and welcome to Energize the Future with Advanced Battery Testing Solutions. Today we will focus on elemental analysis of battery raw materials with ICP, EDXRF, and TOC technologies, focusing in particular on how the unique challenges posed by various lithium-ion battery components can be overcome with sample preparation, software, and with optimized analytical conditions. We have some great speakers today. Dr. Joel Langford will discuss EDXRF and ICP. Dr. Haihan Chen will detail ICP and ICP-MS applications. And finally, Keith Long will discuss TOC. I am John Peters, and I will be your moderator. A bit about Shimadzu as a whole. Shimadzu Corporation was established by Genzo Shimadzu Sr. in 1875. Early innovations included a manned hydrogen air balloon and early X-ray inventions. Shimadzu is now the second largest instrument manufacturer globally, with about $3.6 billion per year in revenue and growing. Shimadzu Scientific Instruments was established in 1975 and consists of 10 regional offices covering the United States, as well as multiple instrument dealers covering Canada, Mexico, the Caribbean, and Central South America. Headquarters in Columbia, Maryland is where the marketing and product groups, applications, and a large demo lab exists. Each regional office also has a demo lab as well as local sales, tech support, and service. As such, Shimadzu's product portfolio is a comprehensive array of technologies to serve multiple industries, all of which are relevant to various parts of the battery economy and value chain. Technology categories include informatics with lab solutions, molecular spectroscopy, elemental spectroscopy, chromatography and mass spec, physical testing, single element analysis such as TOC, and non-destructive CT scanning. This chart is from the Shimadzu Guide to Lithium-Ion Battery Solutions and details the various parts of a lithium-ion battery, of what materials this part typically consists, the commonly used chemicals of those materials, and what technologies are used to characterize each. The list of instruments shown here are all available through Shimadzu Scientific Instruments in the United States with local service and support. Most of the technologies in the SSI portfolio are relevant to batteries, but today we will discuss applications for the highlighted technologies in green, elemental analysis, and TOC. And now I'd like to turn it over to Joel Langford.
Hello, everyone. In this portion of the webinar, we will be discussing energy dispersive X-ray fluorescence spectroscopy and its applications with regards to analyzing battery-centric materials. As such, this slide is an introduction behind the working principle of energy dispersive X-ray fluorescence, also known as EDX. In EDX, you have an X-ray tube that emits a polychromatic distribution of X-rays. These X-rays impinge on the sample. The atoms within the sample are electronically excited by the X-ray beam. As a result of this excitation, the atoms decay, which results in the production of what is known as a fluorescent X-ray photon. The fluorescent X-ray photon energy is dependent upon which element it came from. For example, the aluminum photon energy, X-ray fluorescent photon energy, is 1.48 kiloelectron volts. Chromium is 5.4 kiloelectron volts. You can use an energy discriminating detector to procure a spectrum, an energy dispersive spectrum, where on the x-axis you have energy that is used to distinguish between different elements, and on the y-axis you have intensity, which is used to gauge the nominal concentration of that element within the sample. To summarize, EDX is a non-destructive elemental analysis technique that measures the elemental composition of a sample on the scale of roughly 1 to 30 minutes. The following is a more concrete overview of what an EDX actually looks like. Again, in an EDX spectrophotometer, you have an X-ray tube that emits a polychromatic distribution of X-rays. In between the sample and the X-ray tube is a series of filters that is used to increase sensitivity for a particular range of elements, followed by a collimator, which is used to choke down the X-ray beam to a particular area of interest on the sample. To align the sample with the X-ray beam, we use a CMOS camera, which is below the sample. You can see in the following pictures that They're the CMOS camera in actual action. For example, in the bottom right is a glass shard with a yellow ring on it. That yellow ring is the actual 1 mm collimator exposure area of the X-ray beam on a piece of glass. Since EDX is a non-destructive technique that requires very little sample preparation, a variety of sample types can be measured, including powders, liquids, and solids. For example, the stapler that is inside the EDX sample analysis chamber. The EDX has a footprint of roughly that of a laptop computer, with the energy consumption of one. All that is needed to operate an EDX is a computer and a 120-volt outlet. There is an LED light on the EDX to indicate when X-rays are on and when X-rays are actually impinging on the sample, i.e. analysis is occurring. During analysis, the sample chamber is locked such that it can't be opened by anyone. The sample chamber dimensions are also pictured. Provided that the sample is smaller than the sample chamber dimension, it can be measured by the EDX. In other words, as long as the sample fits inside the sample chamber, it can be measured by an EDX, even with a turret installed. Shimatsu's EDX 7200 can measure elements from sodium to uranium on the periodic table. As you get heavier in atomic mass, the detection limit improves. For example, the detection limit for sodium is roughly 100 ppm. For third row transition elements like titanium, vanadium, and chromium, the detection limit is roughly 1 ppm. As you get into the heavy metals like mercury, gold, thallium, and lead, you get sub-ppm detection limits. What I want to recapitulate is that EDX is a non-destructive technique that measures materials in their native state. So all these materials can be measured by EDX in a non-destructive, native type fashion. In the following slides, we will be discussing the analysis of black mass by EDX. The following is a typical sample preparation process for a black mass, a powder sample, or even a liquid sample. You would take your powder, and for example, you would take a scupula and put that powder into what is known as a XRF cup. The powder sits inside the cup and is supported by a transparent X-ray film that is made of a material like polypropylene or mylar. You would take the cup, and provided that the EDX has a sample turret, you can load the turret up with up to 12 samples and then hit the start button. Note the simplicity of this process compared to other analytical technologies. Anyone can easily do this. Also note that the consumable cost is very low in this process. In this case, all you have is the sample cup and the film. In this example, we have loaded the turret with a variety of electrolytic solutions and salts. Each sample was analyzed with what is known as a survey scan, which covers the periodic table of from sodium to uranium. In this case, the survey scan takes approximately 3 minutes per sample. Note that even without a method that implements external standards, you can still get an idea behind the elemental composition of your material. In this case, we call the data semi-quant data because it was procured without the use of external standards. One nice feature of EDX is that it is still possible to get an idea behind the elemental composition of your material even without the implementation of standards. In this webinar, we will also be discussing other analytical technologies such as ICPE. ICPE compared to EDX is an excellent quantitative analytical tool. However, prior to analysis, the sample must be a liquid. So if you are analyzing a solid, it must be digested into the liquid state. ICPE is more consumable intensive compared to EDX, and calibration is more frequent compared to EDX. Comparing EDX to ICP, EDX is useful for applications like fast screening. There's very little to no sample preparation, and as there's not as much of a need to calibrate. Curves last a long time on an EDX compared to an ICPE. The downside of EDX is it's not as quantitative as ICP, namely because you are measuring samples in their native state. So competing matrix effects can become prevalent in EDX compared to ICPE. However, you can imagine a scenario where we use the ICPE to calibrate the EDX. What I will show in the following is taking black mass samples, measuring them on the ICPE, and taking the ICPE data to calibrate the EDX, thereby making the EDX a more quantitative analytical tool similar to that of an ICPE. On the top row, we denote those correlation graphs as standardless EDX. For example, in the top left, we have a correlation graph for aluminum. On the x-axis is the ICP result, and then the y-axis is the EDX result without calibrating using the ICP data. For example, in the aluminum graph, you can note that the highest concentration aluminum is nominally 3% as detected by EDX, and it's nominally 2.4 to 2.2% for the ICP. Again, as I mentioned previously, EDX can be used to get an idea behind the nominal composition of your sample without standards, a process called semi-quantification, semi-quantitative. The red dotted line is the regression in the graph between the EDX result and the ICP result. The gray line would represent a perfect correlation between the EDX and the ICP. On the bottom graph, the EDX results were calculated using the ICP data. In other words, the ICP was used to calibrate the EDX. We call this an external calibration using the ICPE. Note the remarkable improvement in correlation between the EDX and the ICP data, especially in the range of element concentrations being measured. In other words, the red dotted line has a high degree of overlap with the solid gray line, especially in the range of element concentrations being measured. Similar to the graphs previously shown, the numerical data also indicates that calibrating the EDX with the ICP results in an increased degree of analytical accuracy. The top box is the standardless EDX recovery. Notice for elements like aluminum, sulfur, and phosphorus, the recovery is quite poor, or basically, in other words, the degree of correlation between the EDX and the ICP is quite poor. However, when you use the ICP to calibrate the EDX, the recovery improves, as indicated by, for example, the green colored boxes in the aluminum and the phosphorus and the sulfur columns. Turning to yet another application, and that's raw material identification and contaminant identification by EDX analysis. Often in a manufacturing environment, a supplier will provide a raw material. It is often necessary to validate the raw material is what it says on the label, a process called positive material identification. There's a multitude of analytical techniques that can achieve this task, but the two that stand out are EDX and IR. Both are quick and easy to use, are non-destructive. In addition, EDX is much more sensitive for inorganic materials, while IR covers the more organic and is more sensitive towards the organic realm of materials. In addition, there's also contaminant analysis. For example, on a manufacturing line, there could be an issue that's associated with a contaminant. That contaminant can be isolated and, like the raw material, can be analyzed by EDX and IR and further understood. With that in mind, Shimatsu has developed a software package known as EDX-IR. The idea behind EDX-IR is to validate a contaminant is what it is or a raw material is what it is. The idea is you run a sample on the EDX and the IR and you compare it to a list of known samples using a search match algorithm. The search match algorithm procures what is known as a hit list, which provides a list of candidates that are most similar to the material in question. This hit list can either be contaminants in nature or raw materials. Shimatsu has also developed what is known as the EDXIR sample holder. This sample holder is especially useful for contaminant analysis, since contaminants are often low in volume. The idea behind the sample holder is that you put the sample inside of it and you close it like a sandwich. You open it for the IR analysis and close it for the EDX analysis. What's nice is that the same exact sample is being measured by both EDX and IR. In addition, the sample can be easily archived and stored for later use. In summary, EDX is a non-destructive elemental analysis technique that measures elements ranging from sodium to uranium on the periodic table. Even without external standards, the EDX can be used to obtain semi-quantitative data. However, using the ICP to standardize the EDX makes EDX a quantitative tool similar to something like an ICP.
Thank you, Joel. That was a great discussion. I'm sure there will be many questions. Let's hear from Haihan Chen now.
Thank you, Joe. Elemental analysis is an important step in the battery production process to ensure quality and performance. It's used at various stages of the battery value chain. As shown in the picture on the left, during mining and raw materials production, elemental analysis help identification and quantification of elements in raw materials such as ores and brines. During battery manufacturing process, elemental analysis is used to measure impurities in anode, cathode, and electrolyte materials. It's important because the impurities in batteries affect battery performance and lifespan. Manufacturers are also required to monitor element and organics of any discharge from their factories to comply with regulations. During recycling, understanding the elemental compositions of used batteries is crucial for better separation and recovery of those valuable elements. During this section, I will show how inductively coupled plasma optical emission spectroscopy, or ICP-OES, and inductively coupled plasma mass spectrometer, or ICP-MS, are widely used to analyze battery samples. While elemental analysis is used at different stages of battery production, those battery samples are very difficult to measure compared to drinking waters or other common sample types. For example, samples usually has very high total dissolved solids. Sometimes they have organics, they have fluoride. The element in the battery samples have very wide range of concentration. You might see high concentration of lithium, cobalt, nickel, manganese, and low concentration of other elements. The samples all usually has very complex matrices with high background signals and various interference. It also contains easily ionizable elements such as lithium, potassium, and sodium. All those different factors can affect the accuracy and precision of analysis results. First, let's look at inductively coupled plasma optical emission spectroscopy, or ICP-OES. The ICP-OES uses the fact that atoms and ion can absorb energy to move electron from the ground state to an excited state. In ICP-OES, liquid samples are dissolved, vaporized, atomized, and excited in an argon plasma. When the atoms at excited state fall back to the ground state, it emits light at its characteristic wavelength, which is then collected by a detector. The wavelength corresponds to the specific element, and the light intensity at that wavelength is proportional to the concentration of that specific element. This is very similar with the flame test experiment we did at high school, as shown in the picture on the right. By burning different elements, we can see different colors of flame. For example, sodium shows a yellow-orange flame, lithium shows a red flame, and copper shows a green flame. Compared to other elemental techniques, ICP-OES provides great sensitivity. It can measure a lot of elements down to ppb detection limit. It has great tolerance on sample matches. For example, it can measure high salt samples up to 40% total dissolved solid. It can handle samples with hydrofluoric acid, which is very nasty and can attack glass. It can also be used to analyze organic samples directly. Shimadzu ICP-E9820 DuraView ICP-OES has a good variety of sample introduction systems to accommodate these different sample types. For example, most battery samples have very high total dissolved solid. We have several different types of nebulizers can be used, including sea spray nebulizer and Nordmeyer nebulizer. An argon humidifier can help alleviate clogging issues of torch and nebulizer due to those high salt in the battery samples. We also have different types of torches like organic torch, high salt torch, and hydrofluoric acid torch as shown in the slide. Those torches can be used for different types of samples. Shimadzu ICP-E9820 comes with many features and benefits. First, it's a dual-view instrument, which means you can view the plasma both from the axial and radial directions. In axial view, light is collected from the length of the plasma with a longer optical path length, providing high sensitivity for trace elements. In radial view, light is collected from the side of the plasma, which can be better for analyzing major elements with high signal intensity, which can potentially saturate the detector if we measure those elements with axial view. The dual view provides best combination of sensitivity and dynamic range for simultaneous analysis of trace and major elements. This is a key feature that benefits battery markets because for battery materials, we want to identify major elements like lithium, cobalt, nickel. But in the meantime, we want to analyze the elemental impurities like cadmium, like lead, iron, copper that can negatively affect battery performance. The dual view allows you to run those unknown samples without actual sample prep, saving your time, increasing your productivity, and saving the operating cost. The torch in Shimadzu ICP-E9820 is placed vertically. This enables fast rinsing of the sample introduction system to minimize carryover. Running ICP-OES is very expensive due to the high consumption of argon. A regular size of an argon tank can only last for about a day. Shimadzu adapts a mini torch that has a smaller diameter. The mini torch uses the less argon. It only uses about 2/3 of the argon of conventional torch use, saving the operating cost in the long run. Unlike other ICP-OES systems in the market that needs consistent purge of the optical bench, Shimadzu ICP-E9820 is equipped with a vacuum pump that can run 24/7 to keep the optical bench under vacuum, which means zero consumption of gas in standby and therefore lower running cost. The optical bench is also kept at about 38 degrees C, constant vacuum, constant temperature. This enables quick startup of the instrument with better stabilization and better sensitivity. The Shimadzu ICP-E9820 is also equipped with a CCD detector that captures all of the wavelengths from 167 nanometers to 800 nanometers at one exposure. This allows for reprocessing of data to avoid spectral interference without having to rerun for complex matrices. For example, when you analyze one element at a certain wavelength, during data reprocessing, you realize that the wavelength you selected at the beginning suffers from interference and is not the best one to use. In this case, you do not need to rerun your sample. Instead, you can just go into the method setup and add another wavelength into the method, and the results will show up. This can be realized because the data of a full wavelength has been captured and stored in the data files. This can be extremely beneficial for battery markets because those samples has very complex matrices with high backgrounds and various interference. So you do not lose time having to rerun those samples and get buried by a backlog. As you can see, ICP-E 9820 is a robust and reliable instrument to enhance your instrument's uptime, reduce quality control failure, save operating cost, improve laboratory productivity, and provide you greater confidence in data accuracy. With all the benefit of ICP-E 9820, let's take a look at some of the data it's produced for battery materials. First shown here is the analysis result of bright mass materials. The growing battery market depends on a global supply of essential metals like cobalt, lithium, manganese, and nickel. Meeting these demands require a sustainable approach and increasing needs for recycling. The most common recycling technology is to render batteries and electronic components into bright mass powder by physical and thermomechanical processing. These result in a complex mixture of organics and inorganic materials. Analyzing these can be challenging because of the high total dissolved solid, extremely wide range of concentration from ppt to tens of percent levels, the insolubility of the materials in acids, the presence of electrolyte solution residues, organics, and halides. The analysis technique detailed in this study utilized a specific sample preparation and digestion technique and various software features to overcome this challenge. Bright mass from a local battery recycling plant was digested in a mixture of hydrochloric acid and nitric acid. The digested sample is then analyzed with ICP-E 9820. The figures on the left shows typical calibration curves. The table on the right shows analysis result. A total of 17 elements was measured. The major elements include aluminum, calcium, cobalt, lithium, manganese, and nickel was measured with radio view, and other elements was measured with axial view. The linear regressions are all higher than 3.9. This indicates good linearity for the selected wavelengths. The instrument detection limit and limit of quantification are all shown in the last two columns of the table. As you can see, ICP-E 9820 provides great sensitivity for all the target elements down to ppb levels. The second study shown here is for analysis of elemental impurities in the graphite materials with ICP-E 9820. Graphite is the most common lithium-ion battery anode materials, but testing it for elemental impurities poses various challenges. Graphite is not soluble in acid and requires a specific microwave digestion protocol, which is detailed in this study. Additionally, many different unknown elemental impurities may be present in the graphite sample in unpredictable and wide concentration range. These could be missed easily with other technologies if not specifically checking for each specific element. The Shimano ICP-E 9820 allows for a full range wavelength acquisition that can be very useful for this complex sample. With the full range wavelength data, you can easily identify and qualitatively measure all impurities present in the sample. Additionally, If a multi-element calibration standard was used during the method setup, element that was physically in the calibration standards but not selected for analysis in the method can be reprocessed and quantified after the samples are run by creating a new calibration curve using the existing data file. Dual view and high salt tolerance of the instrument also allow for a wide dynamic range by selecting radial and axial for different elements, which is also possible to change and reprocess post-run. In this study, because we analyzed elemental impurities, which are trace elements, axial views was used for most elements except lithium and sodium, which was measured with both radial and axial view. By comparing the detection limit of lithium and sodium measured with two different views, we can easily see the axial view greatly increase sensitivity and lower the detection limits. Spiky samples was also analyzed with both low and high concentrations with a spike recovery in the range of 96 to 102%, indicating great accuracy of the analysis result obtained by ICPE 9820. Similarly, cathode materials contain unknown elemental impurities that may be present in wide concentration range. Here we highlight the versatilities of the ICPE 9820 system using the commercially available multi-element cathode materials lithium, cobalt, nickel, manganese oxide. Since the cathode materials contain a large amount of lithium, cobalt, nickel, and manganese, spectral interference from these major elements might compromise analysis of elemental impurities. For this reason, it's important to select the best wavelength that is interference-free. Take zinc as an example. The ICPE solution software recommends 3 best wavelengths to choose to quantify zinc, as highlighted in the red box of the upper left figure. As shown in the lower figures, the software allows users to check which element has peaks that are likely to overlap with target element using the peak search function. In addition, the all wavelength data acquisition function allows wavelength to add after the fact. As shown in the lower figures, the peaks of nickel and cobalt overlap with zinc at 202.548 nanometer, and the peak of nickel overlap with zinc at 213.856 nanometer. These two wavelengths are not suitable to be used to quantify zinc in these cathode materials. But if we look at the upper right figure showing the profile of zinc at 206.200 nanometer, it's free from interference and is therefore the best wavelength to use to quantify zinc. As you can see, the software provides a good variety of functions to choose. You can choose those functions to select the best wavelength to quantify your target element in very complex matrices. Once the best wavelengths are selected for each element, it's important to also ensure the stability of the system over long periods of time, because many of the elements in cathode samples are in high concentration. Salt buildup of various components of the ICP can cause signal instability. Here, we demonstrate robustness of the system over a 2.5-hour period, as shown in the lower left figure, and the small relative standard deviation of the measurement taking over 5 days, as shown in the lower right table. Radial view was selected for the major element due to the wide range of linearity and because the abundance of this element did not require ppb level detection limits. Alternatively, axial view was selected for the minor element of cathode material in order to quantify low levels of contamination and other materials present in the solid. Critical here are the spike recovery rate that's in the range of 95 to 106%, as shown in the last column of the table on the left, demonstrating the accuracy of this analytical protocol. Detection limits are also calculated as shown in the third column of the table. As you can see, many of the elements have a detection limit lower than 1 ppb, demonstrating the low detection limit and great sensitivity of this instrument. Also shown here is the disjections and sample preparation technique in the lower right figure, which is unique for this matrix. The last data set shows analysis of electrolyte of lithium-ion secondary batteries. This is a very challenging sample because electrolyte of lithium-ion secondary batteries are typically composed of lithium hexafluorous phosphate dissolved in an organic solvent, requiring an injection system for organic solvent. However, lithium hexafluorophosphate can hydrolyze to generate hydrofluoric acid, which attack glass-based injection system commonly used in ICP-OES. Lithium is an easily ionizable element that also compromises analysis result. Therefore, in this study, you can see that in the picture, a hydrofluoric acid resistant injection system and the organic solvent torch was used to analyze elemental impurities in lithium-ion secondary batteries electrolyte. The analysis results are shown in the table, giving the complex matrices with organics, fluoride, and lithium. ICPE 9820 can still get great results. The recovery of spiky samples are in the range of 89 to 107%. If higher sensitivity than what ICP-OES can provide is required, ICP-MS can be used. ICP-MS provides high sensitivity, high sample throughput, and high dynamic range. Shimadzu recently released the new ICP-MS 2040 and 2050 series, which won the Red Dot and IF Design Awards. The new ICP-MS 2040-2050 series has a lot of great features. It has exceptional detection limit with newly designed mini torch. It has an argon gas dilution function with preset methods to dilute sample online up to 100 times. It has an echo mode and mini torch for lowest argon gas consumption available in the market. So similar with ICP-OES, the ICP-MS 2040-2050 also has a mini torch that has a smaller diameter. With a smaller diameter torch, it uses less argon to save the operating cost. It has a newly developed reaction cell for improved detection limit for difficult elements. It also has a charge stabilizer to improve signal stability for long-term analysis.
Thank you, Haiyan. That's really interesting how the ICP can be configured to handle such a wide range of different sample matrices. And with that in mind, let's turn it over to Keith Long to discuss TOC.
In this part of the webinar, you will learn about TOC analysis and how it can be used for the battery market. Let's first start by defining what TOC is and how it is measured. TOC, or total organic carbon, refers to carbon that can be found in water, wastewater, and even solid samples. It is indicative of any carbon-based impurity found in these types of samples. There are specialized analyzers that have been developed to measure TOC, and basically these analyzers oxidize carbon in the samples to CO2, which is then measured by either an NDIR, a non-dispersive infrared detector, or a conductivity detector. These analyzers also have built-in mechanisms to speciate out organic carbon and inorganic carbon, making it possible to measure and report only the organic carbon present in the samples. It is important to understand that TOC measurement is quantitative, not qualitative, meaning that it can only determine the amount of carbon in a sample, but cannot determine what type of carbon it is or where it came from. TOC measurement is a very useful method for quickly determining the amount of organic pollution found in these samples. There are basically two different types of TOC analyzers, and they differ in how they oxidize carbon to CO2. First, combustion analyzers use high temperature and sometimes a catalyst in the presence of oxygen to oxidize carbon to CO2. The other type of analyzers are referred to as wet chemical analyzers because they use a wet chemical reaction with an oxidizer solution, UV light, and sometimes small amounts of heat to oxidize carbon to CO2. This presentation will focus on combustion TOC analysis because it is a preferred method for measuring the organic carbon content in difficult matrices often found in samples pertaining to battery research and development. For certain types of samples, combustion analyzers offer distinct advantages over wet chemical analyzers. They offer a much larger dynamic range for measurement, making them ideal for a wider range of samples. They also require less sample for analysis, which means they will generate less waste. This is very important if there is limited sample volume to work with, or if the samples are hazardous and require special processes to dispose of the waste. Because combustion analyzers use high temperatures, they are better for fully oxidizing samples that contain particulates and salts that wet chemical analyzers may have trouble with. These salts and particulates will also become trapped in the combustion tube, allowing for accurate low-level measurement of carbon in these types of difficult matrices. In addition, total nitrogen analyzers or detectors can also be used with combustion TOC analyzers to measure the nitrogen content in samples. Shimadzu has been the world leader in the manufacture and sales of TOC analyzers since 1967. More than 40 years ago, Shimadzu developed a high-temperature catalytic oxidation method for measuring organic carbon, and in 1983 we released the TOC 500, revolutionizing the industry and setting the new global standard for TOC analysis. This method is still used today, and Shimadzu has continued to build upon this technology with its most current model of analyzer, the TOC-L. Shimadzu did not stop with just improving upon the combustion TOC analyzer. We also developed and engineered many accessories and new technologies to improve upon TOC measurement for a wide variety of sample matrices and difficult applications. With the addition of the SSM 5000A solid sample module, it is possible to measure the carbon content of solids and slurries. We have two different styles of autosamplers that can be used with the TOC-L to fit any lab's needs or to automate analysis and speed up sample throughput. We have also developed a unique style combustion tube called the high salt combustion tube and additional scrubbers that allow the TOC-L to analyze difficult sample matrices such as high salt or brine samples, high suspended solid samples, highly acidic samples, and even samples that contain high levels of halogens. The Shimadzu TOC-L provides many benefits over other TOC analyzers. It offers the best combination of sensitivity and linear dynamic range with detection limits down to 4 parts per billion for liquid samples and 1 microgram carbon for solid samples. It can perform one analysis in about 5 minutes or less, allowing for quick, real-time monitoring of processes. The standard 5 ml syringe found inside the instrument allows for intelligent dilution of samples up to 50 times, enabling the instrument to dilute out difficult sample matrices, thus extending the lifetime of the combustion tube and other consumable items in the instrument such as syringes, valves, and scrubbers. As mentioned earlier, there are also two different style autosamplers available. The ASI-L is more of a traditional style autosampler, and it can hold up to 93 sample vials. It uses standard size vials in 9, 24, or 40 ml volumes, and the 24 and 40 ml vials can also be fitted with cap and septa. It has an option to add on a stirrer module to stir samples that contain particulates, thus ensuring that a homogeneous aliquot is pulled into the instrument for each measurement. The other style autosampler, called the OCT-L, is basically a valve with 8 tubes coming off of it for sampling. You can connect 2 of these in series for a total of 16 sample positions, and it can utilize any style sample container or flask. The valve and tubing found inside the OCT-L is made of Teflon, so it is ideal for acidic or corrosive samples that may damage components in the ASIL autosampler. The TOCL can be controlled by our all-new Lab Solutions TOC software, making CFR Part 11 compliance effortless. It has secured databases for data, metadata, and audit trails. Also includes functions for reviewing and signing of data files. Data from multiple TOCs and even other Shimadzu instruments can be managed together in one centralized location. So how can Shimadzu TOC analyzers be used for battery research and development? First, it can be used to measure the carbon content in metal powders used for lithium-ion battery electrodes. It is important to use the highest quality materials to produce the most efficient batteries, and TOC analysis can be a quick and accurate way to measure the purity of the lithium cobalt oxide. In one study, Shimadzu used the TOCL and the SSM 5000A solid sample module to analyze commercial lithium cobalt oxide powder. First, a small amount of the lithium cobalt oxide powder was measured by the instrument. Then 3 separate aliquots of this powder were spiked with glucose to obtain an added carbon concentration of 0.2%, 1%, and 5%. These samples were then measured by the instrument in the same manner as a raw lithium cobalt oxide powder. As you can see in the resultant data, the lithium cobalt oxide samples spiked with glucose produced results consistent with the amount of carbon spiked into the powder, while the raw lithium oxide powder showed there was no carbon in the raw powder. These results prove that the TOCL and SSM 5000A can accurately measure the amount of carbon present in lithium cobalt oxide powder. Second, the TOCL analyzer can be used to measure the organic carbon content of lithium brine solutions. One way to obtain lithium for use in the production of batteries is through a process known as direct lithium extraction, or DLE. In this process, lithium is extracted from solutions such as oil-filled brines, geothermal brines, or high-impurity salars through such methods as ion exchange, absorption, solvent extraction, or even membranes. For many of these techniques, it is very important to know the organic carbon content of these lithium brine solutions. For this analysis, the TOCL instrument was equipped with the high salt combustion tube and additional B-type halogen scrubber. 2 different lithium brine solutions were first measured neat by the instrument. Then, an aliquot of each sample was spiked with 15 ppm organic carbon and analyzed in duplicate by the instrument. The percent recovery of the added 15 ppm organic carbon was within 12% of the actual value, proving that the instrument can accurately recover organic carbon in lithium brine solutions. The replicate measurements of the spiked solutions were nearly identical, indicating that the measurement of the lithium brine solution is also reproducible. We did another study to test the long-term performance of the TOCL measuring brine solutions. As you can imagine, brine solutions can be very tough on the instrument, especially for the combustion tube and the consumable items such as the syringe, valve, and scrubbers. For this test, a 28% sodium chloride brine solution was prepared and then spiked with 5 ppm organic carbon and measured 220 times by the instrument. In addition, a blank sample and a 10 ppm organic carbon check standard were measured initially before the 5 ppm brine solution, and then again in the middle after 110 measurements, and at the end after 220 measurements of the 5 ppm brine solution. As you can see in the results, this proves that the TOCL instrument is capable of accurately measuring the organic carbon of brine samples.
Great presentations. Thank you very much. And it looks like we have some time for questions from the audience. So let's start. This question is for Joel about EDX. We see that interference from atmosphere can affect analytical results, especially with lighter elements. What options exist on the EDX 7200 for this?
Yeah, I actually didn't have time to cover the use of vacuum or helium in EDX analysis. However, to the observant viewer, there may have been a slide or two that might have caught your eye that said that the EDX could be used with vacuum or helium. So the answer to the question is yes. the EDX can be installed with a helium kit or a vacuum kit or both. Now the question comes up, why use the helium kit or the vacuum kit? And that really has to do with the analysis of light elements, particularly at ppm levels. And when I mean light elements, I mean elements above the third row of the periodic table. So elements like sodium, magnesium, phosphorus, sulfur, chlorine, those type of elements. Often it is necessary to remove the air from the chamber for light element analysis. Now, why use helium versus vacuum? That depends on the nature of the sample. For liquids, you obviously do not want to vacuum them. They'll simply disappear in the vacuum. So you have to use helium. For solids and pressed powders, pressed pellets, you can use vacuum. That's not an issue. So depending on what type of sample type you have, you may want to consider analysis, and whether you're doing analysis on light elements, especially at ppm levels, you may want to consider either using helium to purge the air away from the sample analysis chamber or vacuum.
This question is for Keith about TOC. The application shown for solid lithium cobalt oxide shows some peak splitting and tailing asymmetry. Is there a concern about this with TOC analysis?
So, yes, that is not uncommon. Peak area integration and precision definitely is critical, but however, peak shape is not. Unlike LC or liquid chromatography, we are measuring the combustion process, which can vary depending on sample size, reaction kinetics, etc. So really it's a combustion profile. The most important thing is that the instrument captures all the CO2 converted from carbon in the sample, not so much the retention time or peak symmetry, etc.
Another question for Keith. What are some of the differences between high sensitivity and normal sensitivity catalysts, and how do they achieve different detection limits?
That's a great question. So the active ingredient in both catalysts is platinum, with the regular catalyst being platinum-coated alumina beads, and the high sensitivity catalyst being platinum-coated wool. So the platinum-coated wool offers lower detection limits because you can actually inject more sample onto that catalyst. It has more active surface area. So you can inject up to 2,000 microliters or 2 mils. More sample equals lower detection limits. Now the regular sensitivity catalyst can only handle injection volumes up to 150 microliters. Anything greater than that can cause the beads to shatter and literally turn to dust in the combustion tube.
A question for Haihan about ICP. You provided some detail about both ICP OES and ICP MS. Which instrument is better for these battery applications, and why?
Okay, so both ICP-MS and ICP-OES can be used for elemental analysis for batteries. But generally speaking, ICP-MS is more used for measure trace level or ultra trace level of impurities due to its higher sensitivity. But the downside of ICP-MS is that it has less sample tolerance. For example, if the sample has a lot of salt, the salt can deposit on the combs of the ICP-MS and affect your analysis results. But ICP-OES has much better sample tolerance. It can measure high salt samples with very high total dissolved solid up to 40%. So yeah, if ICP-OS could not reach to the detection limit you require, then it might be a good time to consider ICP-MS. But if ICP-OS can get what you want, can get to the detection limit you require, then I will stick to the ICP-OS.
Another question about EDX for Joel. The EDX seems to be an efficient analytical technique given the lack of sample preparation, etc. but do you lose some of that with the long analysis time? What are typical analysis times?
This depends on the question or the information that is trying to be obtained. I'll give you a case in point. For positive material identification, often what only matters is the bulk constituents and essentially getting a fingerprint spectrum. You can measure less than a minute worth of analysis time and get a very good positive material identification. However, for more targeted analysis, for example, when implementing the use of a calibration curve, longer analysis time is often necessary. How long is long really depends. First of all, it comes with a little bit of experience. I'll say that. But one of the leading factors is the element that's actually being measured. Like, for example, heavy elements like lead and mercury, even at ppm levels, analysis time is typically on the scale of only a few minutes, something like between 1 to 5 minutes, on average, probably about 3 minutes. However, for lighter elements at the ppm levels, stuff like elements like sulfur, chlorine, at ppm levels, especially, the analysis time can be longer than 5 minutes. It can be as high as 10 to 15 minutes. So it really depends on the information that's trying to be obtained.
And one last question about ICP. A lot of data was shown, and this question is how were the detection limits calculated? How were they determined?
The ICPE solution software automatically calculates and displays the detection limit using the standard deviation of 3 replicate of blank samples and the slope of the calibration curve. We also have customers who run like 7 to 10 method blank sample and then calculate the detection limit based on the standard deviation of these multiple method blank result. Besides detection limit, there are other ways to check the data quality. Like you can look at the linear regression of the calibration curves. You can spike your samples and check the spike recoveries. You can also check the relative standard deviation of your samples.
All right, everyone, thank you very much. We're about out of time. If there was any questions that we weren't able to answer, we will get back to you via email. Of course, you can reach out to any of us offline. And of course, also visit our website. We'd be happy to answer questions. Thank you very much.